In this video, we're going to get some more practice finding derivatives using logarithms. Here, we're going to find the derivative of y equals t times natural log of t squared. So notice when I was reading that, I said times, which means multiplication. Multiplication means we're going to need to use our product rule. I also have an expression, not just a variable, a single variable squared, but I have an expression squared, which implies that I will need to use my chain rule. And then I see a natural log, so I need to know the derivative of a natural log. And I'll write that as a note over here. d dt, this is something we know of natural log of t, that's going to equal 1 over t. All right, so looking at this, we have our product rule first. And our product rule, the derivative with respect to t of, say, a first times a second, remember, is first second prime plus second first prime. So dy, derivative of y with respect to t, my independent variable, is the first t times the derivative with respect to t of the natural log of t squared plus the natural log of t squared times the derivative with respect to t of t. So I'll erase that so it doesn't look so crowded, but I used my product rule here. So I have two small derivatives I need to determine. The derivative of t with respect to t using the power rule is 1, so that's going to go away. And here I just need to deal with this. So d dt of the natural log of t squared. What we want to notice when we look at this is that natural log of t is on the inside and we have that squared on the outside. So if I were to simplify this, I would get 2 something to the first, and then I would need to multiply by the derivative with respect to t of ln t, which is on the inside. All right, so I'll go ahead and throw that ln t back in there. In this situation, the derivative of natural log of t, that's going to be 1 over t. So what we end up with is 2 natural log of t times 1 over t. And this expression is what I'm going to have right here. So the derivative of y with respect to t equals t times what I just found, 2 times the natural log of t times 1 over t, plus the natural log of t, quantity squared, and then we said that we would have times 1, which we do not need to write. At this point, we're basically done with the problem. We just use a little bit of algebra to clean it up. So looking at what we have here, the derivative of y with respect to t, you should notice divide by t times t, those are going to go away. And I have 2 times the natural log of t plus the quantity natural log of t squared. As we always talk about factoring, we can factor a GCF here. I think what I've put in the box is fine, but you could take it one step further. Since both of my two terms have a natural log of t, I could write that as 2 plus the natural log of t. For our next example, we're going to differentiate y equals the log of this polynomial argument, 5x cubed minus 11x squared minus x. Now, the last example was natural log, base e, but I want you to make sure you pay attention. We don't have a base written here. When we have log without a base, that represents a common log, and a common log we assume is going to be base 10. Right, so I'm going to throw that base in here for us, just a 10. Even though it didn't start the problem with that 10, we know that it is 10. All right, so if we want to take the derivative of a log term that has an argument other than just x, we know that's going to be the derivative of the argument over the argument. So the derivative of y with respect to x is d dx of 5x cubed minus 11x squared minus x over that argument, 5x cubed minus 11x squared minus x. And because my argument was 10, not e, I need to make sure I write the natural log of 10. So at this point, I just have one easy derivative to take using my power rule. I'll get 15x squared minus 22x minus 1. So my final answer here will be the derivative of y with respect to x is 15x squared minus 22x minus 1 over the quantity 5x cubed minus 11x squared minus x times the natural log of 10. So if we had started this problem and that had been natural log, we would not have this natural log 10 here. But if we're dealing with any base other than e, we're always going to have divide by natural log of the base. All right? Let's do one more example. I'm going to throw some trig in this one. Here we're going to find the derivative of y equals the natural log of secant theta plus tangent theta. So natural log, we do not need to divide by natural log of the base because natural log of the base would be natural log of base e equal to 1. And because my argument is more than just one variable, we know we're going to use the chain rule. So the way I remember this, y prime, is going to be the derivative of the argument over the argument. So that means the derivative of y, in this case it would be with respect to theta, my independent variable, that is going to be the derivative of the argument, so d theta of secant theta plus tangent theta over the argument, secant theta plus tangent theta. We need to take the derivative of the numerator. The derivative of secant is secant theta times tangent theta, and that's something we know. The derivative of secant gives us secant theta, tangent theta. And the derivative of tangent gives us secant squared theta. So the derivative of tangent gave us secant squared theta. Still all over secant theta plus tangent theta. So we have done taking the derivative, but we do need to factor out that GCF in the numerator. I have a secant in each term. So I can factor that out. That's secant theta times tangent theta plus secant theta. Note that is over secant theta plus tangent theta. Here you'll see tangent plus secant over secant plus tangent. Those are the same as addition is commutative. And the derivative here simplifies to secant theta. So dy d theta is secant theta. I hope that helps with your derivative of logarithms examples. We've got one more thing to cover, and those are going to be the derivatives of exponential functions.